Hey everybody, there is no spoon, and it's time for math with Mr. Troy. All right, we are going to start with a system of equations in 3 variables. We're going to use x, y, and z right now. We'll use other variables later as well. This system is written in row echelon form because there is a stair-step pattern where each row has coefficients starting with 1. Today we're going to be focusing on linear systems. Tomorrow we'll focus on nonlinear systems, and we'll go from there. We can utilize what's called back substitution to solve this system of equations. And this is why we're going to want to put systems of equations in this row echelon form, because I am able to figure out what all of the variables are by simply plugging in to the row above it. From the second row and the third row, I can tell that y equals -1. And when I back substitute that into the first row, I get that x equals 1. My solution to this system of equations is an ordered triple, x, y, and z equal 1, -1, and 2. So here's an example of a system in 4 variables. When we get to more and more variables, we're way more likely to say, x1, x2, x3, and x4, as opposed to saying x, y, z, and w. Although we do use both of these. So what I want to see is if you can solve the fourth equation, x4 equals 3/2, and then back substitute to try and solve this. Go ahead, pause the video, give that a try. I'm over here now. Okay, so I got 1, -2, 3, 3/2 as my solution. This system wasn't given in row echelon form because every row didn't start with 1. But if we wanted to, we could write it in row echelon form by, say, dividing the first row, the entire thing, by 4. Or the second row, I should say, and the second row dividing by 6, and the third row dividing by 2, and the fourth row dividing by 2. However, that might not be the fastest way to do the problem, and that's something that we're going to be examining as we go along in this unit. If you have a system that only has 1s on the main diagonal and 0s everywhere else, that is called reduced row echelon form. And the nice thing about it is that we can immediately see our answers, our solutions to the previous problem, right there in front of us. So we're going to investigate, how do I put a system into reduced row echelon form? And if I don't go that far, then how can I use back substitution to solve my system of equations? So the methods that we're going to learn to solve are called Gaussian elimination and Gauss-Jordan elimination. They both follow the same process. But the idea is that by doing these elementary row operations, which you can see on the screen, that you can rearrange the system of equations in order to be in this row echelon form or reduced row echelon form. The difference between Gaussian elimination, which is on the screen now, and Gauss-Jordan elimination only has to do with the end point. So for now, try not to worry about the specifics of that, just how to do what it is that we're trying to do. All right, I'm going to scrunch all of this way down because something that you're going to find out is that all of this is going to take a lot of space. I'm going to start by labeling my rows as R1, R2, and R3. When I'm solving these systems of equations in this manner, I like to use a very, very strict procedure. So the first thing that I am going to do is I'm going to obtain a 0 here. So I am going to add 2 row 2 to row 3. And I'm going to store that in row 3. Your notation might look a little different than this. If you already know how to program in a certain language, you might not like to use that arrow in that particular way, or you might like to look at it a different way, and that is a-okay. Watch what happens when I do that. So the first 2 rows are going to stay the same. In the future, we will tend to do 2 moves at once in order to kind of speed up the process and eliminate some of the writing. And I now have no x's in this bottom left. The next thing I'm going to try and eliminate is the middle left. So I can do that by adding row 1 plus row 2. And I'm going to put that in row 2. So here's where we're at so far. Now you might hear me slip up every once in a while and say that I'm going to subtract a row, or maybe that I'm going to divide something. But we really always do want to say that we are going to multiply by a non-zero constant. So we're going to try not to say divide by 2. We're going to try and say multiply by 1/2. And we're going to try and say add a multiple of one equation to another equation. So I'm not going to say subtract row 3 from row 2. I'm going to try and say add the opposite. So the next thing that we're going to try and do is we are going to try to eliminate this y. And I can do that by taking row 3 and adding the opposite of row 2. And I'm going to store that in row 3. So as you can see, my approach was to first eliminate this position, then to eliminate this position, then to eliminate this position. That's going to give me this stair-step pattern. And then after I do that, I want to change each of these leading terms' coefficients to 1. So for example, I want to multiply 1/3 times row 3 and make that my new row 3. So at this point, my system is in what's called a row echelon form. Now, there are an infinite number of row echelon forms. It's not like there's only one way to do this, but I can see that one row starts off with x, one row starts off with y, and one row starts off with z, and each of those have a coefficient of 1. Now, I can do that back substitution that we practiced earlier. I'm going to pause the video and have that pop in as movie magic. Before we go on, though, before I do that, make sure we understand, why did I do 2 times row 2 plus row 3? Well, because 2 negative x's will cancel out 2x. Here, row 1 plus row 2, a positive x and a negative x will cancel out. So first I plug z into the equation above, and I find that y equals, I got 73/3. And then I'm going to go and plug both of those things into the equation above it. So that's what that looks like. And then just solving that using Algebra 1 skills, I get that x equals 212/3. Okay, so here's a system of equations that's a bit of the way there. I want to see if you can figure out how to eliminate this position first, then this position, and then figure out how to solve for z, then y, then x. Give that one a try. A system is called inconsistent when it has no solutions. So, for example, if I started to try to solve this, to eliminate that x, I might say row 3 plus -1 times row 1, and put that in row 3. I'm still going to do this just one step at a time. Eventually, I'll do 2 steps at a time. But it's nice to start slow and not try and overdo it. You know, this is all new to us. So, one of these and -1 of those will cancel out. One of these and -1 of those will become 5y. One of these and -1 of those will be -4z. And one of these and -1 of those will be -2. The next thing I want to do is I want to eliminate this position. So I know that my first row is still going to be the same because I'm not going to do anything to the first row yet. And to do that, I'm going to do row 2 plus -2 row 1 and put that in row 2. So that's going to cancel out my x's, and then row 2 plus -1 or -2 row 1 is going to give me 5y. And then this is going to be minus 4z again equals, so the way I always think about it is one of these minus 2 of those. So that would be 0, right? But then the next row is 5y minus 4z equals -2. This is where the name inconsistent comes from. These two rows are inconsistent with each other. It is not possible for 5y minus 4z to be 0 and -2 at the same time, because 0 and -2 don't equal each other. So that is why that is called inconsistent. Any system that has at least one solution is called consistent. So one solution or infinitely many solutions is called consistent. A system that has exactly one solution is called independent, and a system that has more than one solution is called independent. In class, we will talk about how you would find one solution that would work if your system should have infinitely many solutions. And we'll talk about what it means to be linearly dependent and what free variables are. So what I want you to do is I want you to try and apply that same approach to this and see if you can figure out where the problem comes up. All right, happy mathing. And theme song.